Hey guys, what's going on? My name is Professor Jennifer Hill and I run Divide and Conquer Math, which is a website and YouTube channel dedicated to helping you learn math on your terms. So in this video, this is one of my Studying with the Math Professor videos, and if you've never watched one, I just want to give you a quick overview of kind of what this is about. So in this video, we're going to focus on what I would call like certain applications of derivatives in a calculus class. And so we're going to focus on things like graphing, maximum, minimum. I think I put some optimization in here. So it's kind of everything kind of associated with that. So we'll have, max mins, increasing and decreasing intervals, concavity, sketches, all that stuff. So the way that these videos work is that I provide a practice set of problems along with an answer key that I intend for you to do on your own. Now, the reason that I do this, as opposed to like, say, me sitting here and teaching you, is I have an entire channel where if you are looking to be taught, you can check out those videos and I will teach you. But when it comes time to study for a test, there's really nothing that beats practicing a whole bunch. And so that's exactly why I made this series. So I give you some things to practice along with an answer key, and anything that you don't get right, you can find fully worked out solutions as well as recommendations of what else to study, all in this video. So it's kind of supposed to be more of a one-stop shop. Now, if you've never listened to my video of advice of how you should study for an exam, I will drop a link to that in the description below. With this video, sometimes everybody teaches this content kind of in a different place. So that's why max min optimization problems, they all get their own video. You might have this maybe like as part of another derivatives test, or maybe you have this coupled with L'Hopital's rule. So I have other series if you're looking for more things to study, and I will also drop just a mention of those in the description of this video. So the way that this is going to work, for the first hour, you will see me working on my own stuff, and then after about an hour I'll let you know that the time is up. And that's really just there in case you have trouble getting started. You can just work alongside of me, work on that problem set for an hour, and then that's 1 hour that you can say that you've dedicated to studying. And then you can check through your problems. Anything you didn't get right, you can look in the description and pull up the time marker of the problem that you want to see that you didn't get right. And then from there, you might realize that there's other things that you need to review or study, and I have links to all of that both in the problem set and in the description below. So I'm super curious to know if you guys are using these to study, and if you have any suggestions for me. If you could leave me a like or hit the subscribe button if you find this useful, that would be super awesome. And otherwise, thanks for watching, guys. Let's get started. Hey guys, so I'm going to start going through the problem set. If you're not done, you can hit pause now, or you can always start the studying section over again. Okay, so for the following problems, we have a bunch of things that we need to do. So we need to state any critical points, determine the intervals of increasing and decreasing, determine the intervals of concavity, determine any extrema, state any inflection points, and then graph. So we've really just kind of got to go through all the good stuff here. So starting with number 1. So the first thing that I want to do, actually just to help me graph, is I want to notice what the domain is. So the domain in this case is all real numbers. So I'm just going to note that because I'm going to need that for my intervals of concavity. And then also just for my reference, I want to figure out if this graph has any symmetry. So I know that wasn't asked of me, but sometimes that can be something that is asked of you. And so if I work this out, so notice I plugged in f of negative x and I got the same function back out. So this means that my function is even. So when I graph it, I should expect to see some symmetry. So I'm just going to note that this function is even so I don't forget. Okay, so now let me clear some space. Okay, so going back to the list of things that we need to work through. So now we're going to find the critical points. We're going to determine our intervals of increasing, decreasing. And then we're also going to state any extrema. All those things kind of go pretty well together. Okay, so starting with taking the first derivative. So this, by the way, this is our f of x. I didn't state that, but that's our f of x. The first derivative here is 4x cubed minus 8x. So then if I set that equal to 0, so I have 4x cubed minus 8x, I'm trying to find the critical points. I see here that I can factor out 4x, which will leave me with x squared minus 2. And then if I take this x squared minus 2 and I set it equal to 0, so this is something a lot of people forget about. When you take the square root of each side to solve, you have to take plus or minus. So I actually get plus the square root of 2 and minus the square root of 2. So my critical points then are going to be x equals 0. Don't forget that one, right? So in this factorization right here, this will be x equals 0. And then x equals the square root of 2 and x equals the, x equals the negative square root of 2. Okie dokie. So let me clear some space. Okay, so now I want to create my table so I can kind of analyze my intervals of increasing and decreasing. So, okay, setting everything up. And, okay, so I'm going to use the domain, and then I'm going to kind of line up my critical points. So we're going to go from negative infinity to the negative square root of 2. There's my first interval. Negative square root of 2 to 0. 0 to the square root of 2, and then the square root of 2 to infinity. Okay, so now you'll notice that I rewrote the derivative in that factored form because when I choose test points, I think it's easier to think through it like this. So in this first interval, let's say I choose something like, I don't know, negative 5. Negative 5 is in this interval. So if I plug in negative 5, if I think about it in this form, so this will give me something negative. And then here, so negative 5 squared would become positive 25, and then 25 minus 2, this ends up becoming something positive. So I have a negative times a positive. All I care about is what's the sign going to be. So this will be negative. So this is going to be decreasing. And then moving on to the next interval, so negative square root of 2 is a little bit smaller than negative 1. So if I just think about something like negative 1 in here, so if I plug negative 1 into this part right here, I'll get something negative. If I plug negative 1 into this, I will also get something negative. So negative times the negative will give me something positive. So this is going to be increasing. And then if I choose 1, because the square root of 2 is just a little bigger than 1, so then this will be something positive times now something negative. So this ends up being something negative, so this is decreasing. And then if I choose 5, so this will be something positive times something positive. So then this whole thing ends up being positive. Okay, so I'm going to note these intervals of increasing and decreasing. So let's see. We are increasing from the negative square root of 2 to 0, and then again from the square root of 2 to infinity, and then we are decreasing from the negative infinity, negative square root of 2, and then 0 to square root of 2. 0 square root of 2. Okay, so I've taken care of now my intervals of increasing, decreasing, my critical points. Now, judging from my table, I can also determine my extrema. So going here, so let's see, I'll use green here maybe. So I'm going decreasing and increasing. So this negative square root of 2, I'll note it over here, this is going to be a minimum. And then going from this interval to this interval, so I'm going from increasing to decreasing, so this means that 0 is a maximum. So I'm going to note that here. And then finally we're going from decreasing to increasing, so this tells me that the square root of 2 is also a minimum. So I've just noted all of that. Okay, so I'm going to run out of space, obviously, so we can't continue on with the problems. Let me clear some space. Okay, so now we can pivot to the second derivative and concavity and all that good stuff. So the second derivative, let me change to the white color again. Second derivative here will be 12x minus 8. And by the way, that factors then, I can factor out a 4 to get 3x minus 2. So really I need to know where does 3x minus 2 equal 0. So, oh, oops, I totally forgot the square, didn't I? I knew something looked off. Okay, this would be 12x squared minus 8, and so then you factor that out. This becomes 3x squared minus 2. So I need to find where does 3x squared minus 2 equal 0. Okay, so again, just be careful if you're solving this. So I've got 3x squared will equal 2. So x squared equals 2/3. So then I get x is going to be equal to plus or minus the square root of 2/3. Okay? All right, so these are our potential inflection points, so we just want to do a little bit of testing to confirm that. So let's see, I feel like I'm running out of room here. Let me clear a bunch of space. Okay, so I've just noted those are our probable inflection points, so we need to make another table. Again, we're going to use the domain to kind of dictate all that, so let me just draw the table. So for the sake of time, so I won't make you watch me draw the whole table, but these should be your intervals. And then, okay, so now let's determine signs here. So if I choose something like, I don't know, -4, so if I plug that in, so this will be something positive times something positive, so we're going to be concave up. Then if I choose something like 0, so this will end up being negative, so this will be concave down. And then the last one, so if I choose like 4 again, this will be positive, so we're concave up. Okay, so let's see. I'm going to write concave up. So you always want to state those intervals nice and clearly, even if you have them in a table. It's always good to get in the habit of summarizing what you did. Let's see, concave, let's see, I'll just write concave, con D, okay? So this is negative square root of 2/3 and then the square root of 2/3. Okay, so I don't forget. Okay, so that's a summary, and now just evaluating these, so I can also see I'm going concave up to concave down, so that would mean that this is an inflection point, this negative square root of 2/3, and then concave down, concave up, so we've also got another inflection point. So instead of now having this question mark here, let's change it to an exclamation point. Woo. Okay, so let me clear some space, and actually now let's put all of the information that we found, let's put all of that together. So all in all, here's like everything that we've found. So going through the list, so we have now found our critical points, our increasing, decreasing intervals, concavity, extrema, we found our inflection points. So now we just have to graph. So now what I want to do is for like all these critical points, so I want to plug these back into the original function so I can get a point there. And then say like for the inflection points, I want to do the same thing. I want to plug them into this function because then we know what points to graph. So I'm going to have to get away from this so that I can show you the graph. Okay, so I went ahead and just plugged in all of those points, okay, just so we could approximate them. So I'm going to plot all of these. So let's see. So I'm going to have somewhere around here. Let's see, here and here. So here's my square root of 2 and my negative square root of 2, or the point 0, 0. Negative square root of 2/3. Let's see, it's going to bring me somewhere around here and here. Okay, so I plot all those points, and now I just have to really make sure that I capture like the increasing, decreasing, and the concavity. So that really needs to be what drives everything. So I need to go decreasing, then increasing, then decreasing, then increasing. So that's, let's see, it's going like that. And then also, wait, I should probably review this as well. So when I get to these inflection points, then I need to go from concave up, concave down, concave up. Okay, so let's see if we can do this. So I need to go decreasing, increasing, decreasing, increasing. Concave up, concave down, concave up. Okay, that was everything. So this would be a pretty good sketch of the graph. Okay, so moving on to 2 here, so trig. So people always kind of hate trig functions, but there's some benefits of having the trig functions in some ways. I mean, it's a closed interval, so I think that that's kind of nice. So let's get into this. So I know I need to take a first derivative. Actually, before we do that, you know that I like to determine the domain. So the domain was already given to us, so we're good there. And then just if there's any symmetry, so if I were to take y of, say, negative x, so what would that give me? That would give me negative x times the square root of 3 minus 2 sine of negative x. All right, now BT dubs here. When you have sine of negative x, you can actually just bring the negative out in front. So this will ultimately equal negative x squared root of 3 plus 2 sine of x. So this is the exact opposite of the function that we started with. So that tells us this is going to be odd. So it's just something that you want to note as you go through the graph. It just tells you like this should have symmetry when you draw it. So it helps you with coming up with a goal for how to draw things, okay? Okay, so let me clear some space. And now let's take some derivatives here. So this is going to be just the square root of 3 minus 2 cosine of x. So nice and easy peasy to take that derivative. So then if I set this guy equal to 0, so let's see, I get negative 2 cosine of x equals the negative square root of 3. So then I get cosine of x equals square root of 3 over 2. Okay, so I want to be really clear with this. Solving stuff like this should be stuff that when you're in a calculus class, this should be very straightforward, and I'm going to use the word easy, but with like a little asterisk here. So you are expected to know the unit circle very, very well. Memorize, you're supposed to know it as well as you know your multiplication table by this point. But I notice a lot of students do not, and so questions like this can seem so hard. So if you don't know the unit circle, and if you're looking at this and saying, I have no idea how I would solve this, you've got to memorize that unit circle. I just can't stress it enough. I know that it might not be for a grade, but it's one of those things that will make or break you in a calc class. So now referencing my unit circle, I can see that when do I get the value of square root of 3 over 2? Well, I look at those x values in the unit circle. And this occurs when I'm at pi over 6 or at 11 pi over 6. So even if you have to draw this out to figure this out, I don't think there's any shame in that, but like you definitely need to be very comfortable with drawing this out. Trust me, it will make your life so much easier. Okay, so these are my critical points. So let's clear some space. And now we can create our interval table using this as our domain. Okay, so let me draw the table. Okay, so now I've got all my intervals set up. You can check your table against mine, pause the video if you need to. Okay, so now I need to think through just some different values here. So something that might be helpful if this is kind of messing with your head. So remember, at pi over 6, so if I think about this in terms of this problem here, so this, I have the square root of 3 minus 2 cosine pi over 6. So the way this calculation would work, this gives me square root of 3 times 2 times square root of 3 over 2. And so then that gives me square root of 3 minus square root of 3, okay? So anything smaller than that, anything that is between 0 and pi over 6, this is actually going to give me a value that is going to be bigger than square root of 3. So we might get something like, I don't know, 2 over 2 or something. So you have to be able to think through these kind of details. And I think, again, having that unit circle in front of you so you can think through the x-coordinate, I think that's very helpful. So if you don't have the unit circle in front of you, I highly recommend you stare at it for a second to convince yourself that when I'm in this interval, this value will end up being something negative. Okay. And then for literally every other value from here to here in this interval, these are all going to end up giving me values that when I go through this math here, these are all going to give me values that are going to end up being, like this value here will end up being smaller than the square root of 3. So again, if like this throws you off, you want to stare at the unit circle. Maybe actually force yourself to do a couple of these algebraic calculations to really understand it. So this ends up being positive. And then when we get to this last interval, this ends up becoming negative again, okay? So I can see here what my intervals of increasing and decreasing are. Let me just note those. So you always want to include someplace on your problem where you really clearly state what you want for your intervals of increasing and decreasing. This is a good habit to be in, not just for tests, but honestly, like even when you get into the workplace, even if you have all the work there, people always just want the summary. What was your conclusion? So I always recommend that you write this out. Okay, so now I can also figure out my extrema. So in this case, so I'm going from decreasing to increasing. So this tells me that I have a minimum here. And then I'm going from increasing to, oops, literally the opposite, increasing to decreasing. So then I know I have a maximum here. Okay, so let me clear some space. Okay, so onward. So now I need to get to my second derivative, and I need to switch my color back. Okay, so second derivative, this is going to be 2 sine of x. So nice and easy peasy. So 2 sine of x, where does that equal 0? So again, that's totally a unit circle thing. So you have to keep the domain in mind here. You don't need to include the end points necessarily, okay? So besides the endpoints, we know this will equal 0 at 0 and 2 pi, but this will also equal 0 at x equals pi, okay? So this is probably my inflection point, so I'm just going to put a little question mark there for now. So let me clear some space. And now let's make our table using our domain and this possible inflection point. Okay, so now thinking from 0 to pi, so actually this is where like knowing the unit circle makes this very, very simple. All of the values, all the y values from 0 to pi are going to be positive, so our value of y double, or sorry, rho f double prime, I meant y double prime. All these values are going to be positive, so this is all going to be concave up. And then from pi to 2 pi, all my y values are going to be negative, so this will be concave down. And so again, like I say, always say, so you just want to summarize that, so I can say here that I have concave up from 0 to pi and concave down from pi to 2 pi. Okay. So I'll clear space again. And so now I can go ahead and graph this. I think in this case I can probably get the graph all on one page. So let me just draw a graph here. So here's my graph. I just need to go from 0 to 2 pi. Okay, so now what I need to do is I need to take these critical points, so these points here, and then also this inflection point, and I just need to like plug them into this to find what points we have. So plugging those all in, here are the values I get. Okay, so I went through and I plugged in all of these points, and I actually I took the decimal version of them because just with this square root of 3, like think about it, if you tried to plug 2 pi into this, this would not be a very meaningful expression. 2 pi times square root of 3, I wouldn't know where to graph that, so I think just having the decimal approximation is a little better. So you'll notice I plugged in all of my critical points, my inflection point, and then also the endpoints, okay? So then, let's see, I'll do this by, let's see, what's the highest that I need to go up to? It looks like just up to 10. So let me move this actually so I can give myself a little bit more space. And let's see, this will be pi, this will be 2 pi. Okay, so actually let me draw that scale one more time. Okay, so now I'm going from, let's see, -2 up to 11. It's kind of a funky scale, but that should let me graph all these points. Okay, so now I'm going to plot all these points. Okay, so I went ahead and just did that. So there's 0, 0, there's pi over 6 negative 0.093, here's pi 5.441, 11 pi, and then 2 pi. Okay, so now, let's see, from 0 to pi over 6, I need to be decreasing, and then from, let's see, pi over 6 to really 11 pi over 6, I need to be increasing, and I should have an inflection point somewhere in there, and then I should be decreasing again. So let's see, does this all work out? So yes, it does, right? So I'm concave up here, so that's from 0 to pi, that's where I want to be concave up, and then I'm concave down from pi to 2 over pi. So this totally works. In this particular instance, since our domain was restricted, actually it didn't matter that this was odd, so I guess I didn't need to do that, but I always like to just figure that out. I guess I wasn't thinking all the way. This is a really funky looking function if you were to plug this in. It's a really unique shape. I highly recommend you check it out if you like nerding out on math. And okay, so that covers this one. It's a good trig example. So number 3, so the first thing I always like to do with all my functions is just note what the domain is. So in this case, so I've got this 5th root, so actually this will be fine for all real numbers. So my domain goes from -infinity to infinity. And then I also just like to note in those cases if I have any symmetry. So if I plug -x into this, let's see, I would get x to the 2/5, and then this will give me -x minus 1. So there's going to be no symmetry. So it's going to be kind of a funky looking function is what I would anticipate. Okay, so let me clear some space. And I've talked about these types of functions in lots of other videos actually, because I think that these functions can be, they're kind of like sneakily tricky. So if you look up like 5 different YouTube videos on these types of functions, you'll probably find like a bunch of different ways you could approach them. I'm showing you the way that I think makes the most sense, but if you don't like that, you can always look up other YouTube videos and find other explanations. I don't always recommend that, but you know, I have definitely a certain way that I like to approach this, and that way is to actually distribute this before you take the derivative, because I think it makes taking the derivative easier. So if I take the derivative of this, then I get 7/5 x to the 2/5 minus 2/5 x to the -3/5. And then I've created several videos where I talk about how to deal with this. So my preference is to just factor some things out. So specifically, I would factor out 1/5 x to the -3/5. So then what am I left with? That's going to leave me with x, 7x, just, that's it actually, just 7x, minus 2. That's what I'm going to be left with. Now, if you want to see how to simplify this like I did, I have lots of videos where I break that down, so I will drop some links to that in the description and with the problem set, so you can go back and watch those. This is tricky, and you do have to practice this, and I think this is something you can easily forget, so don't be surprised if you have to go back and review it again. But now, just looking at this, I can really easily pick out my critical points. So I can tell now my critical points. So this does not exist at x equals 0. So I'm just going to note that does not exist at x equals 0. And then my other critical point would be 2/7. Okay. Now, it's interesting to note here that 0 is in the original domain, but when we get to the first derivative does not exist at 0. So that should tell you that when we graph this, something funky is going to happen, okay? So let me clear some space. So I'm kind of cramming everything together, but here's where my critical points are, and then I just wrote the first derivative in these two different ways. I like kind of moving between the two different ways. So now, now we need to come up with our table here. So I'll draw the table. Okay, so you can check your table against mine. I've got all my intervals drawn up here. So now, let's see, if I choose a negative value, so I plug something negative into this, this will be negative, and let's see, this will also be negative, so negative times a negative will give me a positive, so this is going to be increasing. Then from 0 to 2/7, so let's say I choose something like 1/7. So this will end up being something positive, and this will end up being something negative. Positive times a negative gives me a negative. So let's see. And then finally, if I choose something like 4, this will be a positive times a positive, so this ends up being positive. Okay, so I always advocate for, even though you might have this all in the table, make it very clear on an exam what it is that you want your teacher to understand. So summarize all this information so that it's clear you know what your increasing and decreasing intervals are. So I have just listed that. And now looking at this, so we can go ahead and come up with our points here. So this is going from positive to negative. So this is telling me then that 0 is going to end up being like some sort of maximum, but it's going to do something funky, right? Because we know that the derivative does not exist at 0, but it's going to act as a maximum. So we will interpret that in a moment. And then I go from negative, so I go from decreasing to increasing. So that means that 2/7 is going to be a minimum. Okay, so let's clear some space. Okay, and so now we can move on to the second derivative. So this is why I like having kind of everything written out like this in both forms. So now I can take the second derivative. I want to use this form to take my second derivative. So let's see, second derivative. Okay, so this is going to be 14 over 15 x to the, oh gosh, I wrote this as 2/3 this whole time. This should have been 2/5. Okay, sorry, this should have been 2/5, but now this will be to the negative 3/5. Sorry about that. I've got it right on the answer sheet, so just we'll go with it. And then, okay, so now, right, so I was taking the derivative. Okay, so now this will be plus 6, let's see, I gotta start this whole thing over, sorry. Okay, the derivative, 14 over 25 x to the negative 3/5, there we go, plus 6 over 25 x to the negative 8/5. This is pretty wild derivative here. So now if I try to factor some things out, looks like I could factor out, let's see, 2 over 25. So notice 2 goes into both 14 and 6. That's why I'm factoring it out. And then let's factor out x to the negative 8 over 5. And so this will equal 7x plus 3. Okay, I had to think about that for a second. So just as a quick reminder, if you're like, okay, wait, how did she get this? Just like a really quick crash course. So what you want to have happen here is when I take x to the negative 8/5, when I multiply this back in, remember I have to get back to this expression here. So I'm thinking to myself then, really, negative 8/5 plus what is going to give me that negative 3/5. So this is what I cover in another video of like how to think through this. So if I were to work this out, so I would get x equals 5 over 5, so x equals just 1. So that's the exponent. So this x is actually the exponent for this. So maybe instead of calling that x, I should have called it e or exponent or something. But that's the reasoning. Like I said, I have another video on that if you want to see more detail. So now that I have this factored out, so I can see that my possible inflection points, like points I want to pay attention to, are x equals 0. It does not exist here, so I just want to note that. And then also x equals -3/7. So this is the one good thing about this, is that you can really quickly pick out what the points are that you're interested in. So I'm running out of space here, so now I need to make a new table. So let's clear some space. Okay, so now let's create our table. Okay, so this can mess with your brain a little bit, so be careful when you're now working through the intervals. This was messing with my brain. So if I choose something negative here, let's say like -4. So if I plug -4 into this guy here, so remember, you are taking this to an 8th power. So when you take something negative to an even power, that ends up becoming positive. So this value here will be positive, but then if I plug something like very large and negative in here, this will be something negative. So I have something positive times something negative. So the sign of f double prime will be negative. So this means I'm concave down. And then if I choose something like -1/7, so again, this is going to end up being something positive, and then this will also be something positive, because if you think of a value like -1/7, this ends up becoming like -1 + 3. So this ends up being something positive, positive, so this ends up being positive, so this is concave up. And then if I choose something positive, this will be positive times positive, so this is also positive, so concave up. Okay, so what that tells me then is, so -3/7, I'm going concave down to concave up. -3/7 is an inflection point. So this is an inflection point. This is definitely not an inflection point. Okay, so we actually know that the derivative does not exist there, so that makes sense. So everything has to stay concave up around that. So that's going to be a little interesting. Okay, so let me let's see. We've got a lot of information here, and then also you just want to make sure you like. I don't have space here, but I will say that make sure that like on your test or whatever that you state these formally, like write a sentence or make it very clear. It's never enough just to have it in the table. You want to just summarize it someplace very clearly. So I have all of this information now between all of these two slides. Okay, this is a lot. So let me clear some space and let me make a graph. So now going back to all of our critical points and our inflection points, I just want to write those down so I know what to plot. So let me note all those. Okay, so now I've plugged in all my points, so I can go ahead and let me just plot all those. So I've plotted all that, and now I have to make sure that all the stuff I found previously I match here. So I need to be increasing from -infinity to 0, and then decreasing, and then increasing again from 2/7 on. And then I also know that I need to go concave down up to -3/7, and then concave up the rest of the way. So this is going to be a strange looking graph. So let's see, I'm going to be concave down but increasing, and then I need to switch to concave up. Now remember, at 0, we know that the first derivative does not exist, but it does exist on the graph, and this needs to be a maximum. So what's going to end up happening here, so that we can also like maintain the concavity, this is actually going to be what's known as a cusp. Okay, so it's like you kind of have to know when to interpret those. I have a lot of other videos where I do this. So let's see if I can make this look right. So I got a point here, and then let's see, actually from here on, then I need to be increasing. So let me just draw this little leg again. Okay, so you see how here's my cusp. So I kind of hit like this point here. So maybe I've not drawn it as perfectly. Let's see. Okay, so I've tried to draw this as a cusp. So I'm concave up on both sides of it. It is a maximum, but the derivative would not exist here because it is a point. So I've really kind of maintained everything about the graph from the information that I found. So those ones are tough. If you found that difficult, I do think these are pretty tough ones, and these are usually pretty good ones for an exam. So if you struggled with this, I do have other examples of this. I highly recommend that you check them out. But this is definitely a great one to test your understanding of graphing. Okay, so for number 4, so I've got f of x equals x over the square root of x squared plus 1. So just before we get into this, so you know that I like to just consider what is the domain. So usually with the domain, what we're worried about with a situation like this, like a fraction, is where you might get a 0 in the denominator. But notice in this case that these are being added, and then whatever I plug in for x is always going to be squared, right? So even if this were something negative, it would turn into something positive. So the denominator is actually never going to be 0. So the domain in this case then is actually just all real numbers. So I just want to note that to myself. And then the other thing I want to just take a moment to note here, I always like to just examine the symmetry situation. So if I plug in negative x into this thing, I get negative x over the square root of x squared plus 1. So this would be a negative f of x. This is the negative now of my function, which indicates that this function is also odd. Okay, so that's just something for us to note. That kind of tells us a little bit about what the graph should look like. Okay, so let me clear this out. Okay, so next we should probably go ahead and find a first derivative here. And so to find the first derivative, I need to use the quotient rule. So here's my top function, here's my bottom function. So first I take the derivative of the top, which is just 1. I multiply that by the bottom function. And then I subtract this off. I leave the top function alone. And now I need to take the derivative of this function. Now keep in mind you're using the chain rule here. The square root is the outer function. So taking the derivative of the outer function, this is going to be 1/2 x squared plus 1 to the negative 1/2. That's the derivative of the outside. The derivative of the inside would be 2x. So there are all my pieces. And so now we have quite a bit of simplifying to do. So I need to take the denominator still and square it. Okay, so let's simplify this now as much as we can. A lot of times these graphing problems really come down to more algebra. Okay, so in this case, this is going to turn into x squared over the square root of x squared plus 1. All of that over, this will just be x squared plus 1, right? Because when I square the square root, the square root will drop out entirely. So here's what I'm left with. Now, we don't want this fraction here, so what I want to do next is I want to get rid of that. So I will multiply the top and bottom of this entire fraction by the square root of x plus 1, like this, here and here. And then as I distribute this, so think about when I multiply this times this, the square root's going to drop out. And then when I multiply this times this, the square root's going to cancel out. Okay, so let's see. I think I need some space. I'll clear some space. And so now let's go ahead and simplify. So this becomes x squared plus 1 minus x squared. And then this denominator, this will become the x squared plus 1 to the 3/2. So I have multiplied or really added the exponents together. This is the same thing, right? Okay, and so then if I were to simplify this, this would just come out to 1. Let's see, maybe I'll write this on another line. F prime of x is just equal to 1 over x squared plus 1 to the 3/2. Okay, so this problem is actually a little funky. So if I try to find the critical points of this, so the numerator is never equal to 0, right? So top never equals 0. And then the bottom, this is also actually never going to equal 0. We'd have to go into imaginary numbers. So this function has really no critical points. Anything can happen, including no critical points. Okay, so that's pretty interesting. So then if I want to figure out my intervals of increasing and decreasing, let's clear some space. And so this table then, it's like almost comical. This is really just the only interval, right? This function's just going to have one set of behavior. So if I just take any test point in this, so if I write like something like 0, this will just end up being positive. So the whole thing is positive. So this function, my conclusion, is that it's just always increasing. So maybe I'll just note that here. So always increasing. Okay. All right, cool. So now, well, that was pretty simple actually. So now we got to find the second derivative. So I'll clear some space. Okay, so now we're going to take the second derivative. You could use the chain rule here if you wanted. In fact, I think I will even do that. So I'm going to rewrite this first derivative as x squared plus 1 to the negative 3 halves. It's literally equivalent, right? So now if I want to take the second derivative, so I'm using the chain rule, so this becomes negative 3 halves x squared plus 1, and then I subtract 1 from this, so this will become negative 5 halves. And then I multiply that by the derivative of x squared plus 1, so this is just going to be 2x. And now I don't have to mess with the quotient rule. So if I simplify this, see the 2's drop out, so this becomes negative 3x on top, and then in the denominator I get x squared plus 1 to the 5 halves. So now I need to find any potential inflection points. So you're just looking for either where the denominator will equal 0, which we've already talked about it won't, or where the numerator will equal 0, which in this case negative 3x will equal 0 only when x equals 0. So there's my possible inflection point. Probably is, right? Because we know that we don't have any issues with 0 and all the points exist. We've got all real numbers in our domain. So let me clear some space and we'll make a table here. Okay, so in this case for my intervals, so now I'm going from negative infinity to 0 and then 0 to infinity. And I've got my sign of f double prime and then my conclusion. Okay, so if I choose something negative, well, if I plug something negative in, the top will become positive and the bottom will still be positive. So this whole thing ends up being positive. So in this interval, I'm going to be concave up. And then if I choose a positive number to plug into this, then the top is going to be negative and the bottom will still be positive. So the overall value of this will be negative. So this will be concave down. And so this means then that 0, yes, 0 is an inflection point. So I guess I'll erase this question mark. And let's see, I probably want to note my concavity. So maybe I'll just write over here, negative infinity to 0, concave up. And then let's see, I'll write 0 to infinity, concave down. Okay, so let me clear some space. Okay, so over here I've kind of summarized what we just figured out. So now the last thing that we have to do here is graph. So let me draw a graph. And I think the thing about this particular problem, I think this is a little difficult to choose how you want to graph it, because there's not a ton of information that really helps us sketch out the curve at this point. I know that I have an inflection point of 0, so if I plug 0 back into this, I get 0, 0, so I can mark that point. But I don't really have any other like significant points to plug in right now. I know this is concave up, and I know that, so from here to here, concave up, and then from 0 on, concave down. So I have some ideas of how that could look, but you might feel kind of nervous about trying to graph this, okay? And you have to keep all of this increasing too, right? So if you're not sure how that looks, then a last-ditch effort would be to look at this function and think about the end behavior. So let's just take a second to think about that. So I think a lot of times you can get by without doing this, but in this particular problem, you might just be a little unsure. So the best way to figure out the end behavior would be to take a limit. So what is happening with this function as x approaches, let's say, infinity? So for this problem, you have to think now back to your good old limit tricks. This is technically a rational expression, so I can divide by the highest power. And you might also remember, so taking the square root of x squared would kind of just bring this power back down to just being x. So that's the highest power. There's really, like, in some ways, the same power on top and on bottom. So I can divide both the top and bottom by x, but when I divide this denominator by x, instead of calling this x now, I'm going to change this to the square root of x squared. That's equivalent to x, but then this will allow me to do this division. So if I do this division, okay, so if I do this division, I get 1 over, and then this becomes the square root of, this will be x squared over x squared, and then 1 over x squared. And we know that x squared over x squared is just equal to 1. So let me erase this now and just call this 1. Okay, so now if I take this limit as x goes to infinity, the only thing I really have to worry about is this part right here. This is going to go to 0. So I'm left with 1 over the square root of 1. This is just 1 over 1, so this equals 1. Okay, so this is actually very important. This indicates then that we have an asymptote. Wasn't totally obvious just looking at this, but there is this asymptote at y equals 1 as we go towards the positive infinity direction. So this was a worthwhile exercise, and now I want to take a look at what happens as x goes to negative infinity. So I've gone ahead and set this up. So we're going to do the exact same trick, right? So now I'm going to divide everything by x again. So in this case, I've got to divide this by x squared. So it's like the same math, but let's see, this becomes 1 over the square root of, so let's see, this is x squared over x squared. So there is a little bit of an issue here that we're going to have to just be careful with when we do this. So if this is how you set this up, that is correct, but there's like one little caveat with this. So because we're going to negative infinity, we do need to like have that reflected kind of in our work. So the problem is that like what is really happening here when I divide this by this square root of x squared, we kind of need to like put a negative in front here. I know that sounds super weird. This is like something that happens specifically with square roots, but like you need to capture this negativeness, because what's going to end up happening is if I just set it up like this, I end up losing the fact that this is going to negative infinity. Like I have no way to really like bring the negative infinity into this, because I kind of like end up accidentally canceling it out. So what I want to do here is I'm going to put a negative right in front here. And so this works out to be almost the same math then. So this part here will still end up going to 0. But what I get is 1 over the negative square root of 1. So my other asymptote is y equals negative 1. So like I said, like if this is something that you don't usually do, it's not something that you usually even have to worry about. This is something we specifically have to worry about because we're working with the square root of something squared, and we need to reflect that this is negative, is maybe the best way I can describe this. So anyways, so my point is we have these two asymptotes. So if I come back to my graph, so let's say here's 1 and here's negative 1. So this actually gives me some pretty good insight now of how the graph should look, because otherwise I kind of felt like I didn't have much to go on. So I can't cross that asymptote. So now from negative infinity to 0, I just need to be concave up. So I can go like this, and I just need to tend towards that. So there's concave up. Here's concave down. Boom, done. Kind of crazy, right? It's a very simple graph, but I think this one can kind of mess with you a little bit. So for number 5, so I've got y equals the negative, so notice there's a negative here, x squared minus 2 over x squared minus 1. Okay, so this is kind of like your classic rational expression, really. So let's just go ahead and note the domain to start, I guess. So for the domain, so really what we're interested in is where would we get a 0 in the denominator, which, you know, x squared minus 1, this factors as x plus 1 and x minus 1. So at negative 1 and 1, that's where we can't have a 0. So my domain then is going to go from negative infinity to negative 1, from negative 1 to 1, and then 1 to infinity. So remember, a lot of people drop this middle interval, but you really just, you want to keep all the values between negative 1 and 1. You don't want to discard them. So just make sure you have that kind of represented in your domain. So this can make our intervals of increasing and decreasing a little more interesting, possibly. And then if I were to plug in that negative x, so again, I'm just interested, like, do I have any symmetry in this case? So let's see, if I plug in negative x, so in this case I do have symmetry also, right? So this just, it becomes the exact same expression. Nothing changed because we squared everything. So this is also going to be even. So again, it's just something good to know because it helps frame how your graph should really look. Okay, so let's clear some space. Okay, and now it's party time, i.e. it's time to start taking derivatives. So I've got to use a quotient rule here. So let's see. I'm I'm going to transfer this negative just in the back of my mind. I'm going to transfer it to the top function. So actually, before I write y prime here, let's go ahead and just multiply this to the top because I don't want to deal with it. I get very negative, or I get very nervous when I have too many negatives. So now I'm going to think of this as negative x squared plus 2 over x squared minus 1, and now we can start taking the derivative. So I got to use the quotient rule here. So first I take the derivative of the top. So the derivative of the top will be negative 2x, and I multiply that by the bottom. Then I subtract this off, and I leave this negative x squared plus 2 alone, and I multiply that by the derivative of the bottom, which will just be 2x. And divide all that good stuff by the denominator squared. And now I'm going to start simplifying. So I have to be careful when I do this. I have to actually multiply everything out. You cannot cancel this out with this. That is illegal. You could cancel out this x squared minus 1 if this and this both had x squared minus 1, but they don't. So you can't. Okay, so this becomes negative 2x cubed plus 2x minus, and then let's see, this will become negative 2x cubed plus 4x. Do I have that right? Yeah, I have that right. Okay, all of that over x squared minus 1 squared. Okay, so let me clear some space. Okay, and so now if I were to simplify the top, let's see, these 2x cubes actually drop out, and then I'm left with 2x minus 4x. So it looks like the top will be negative 2x over x squared minus 1 squared. So now we have to determine either where does this equal 0 or where does this not exist. So this does not exist at x equals 1 and x equals negative 1. No surprise there. The original function didn't work either. And then this is x equals, this is 0, maybe I'll write it like that, 0 at x equals 0. So that's where the denominator would equal 0. Okay, so now we can go ahead and clear some space and we can start finding our intervals of increasing, decreasing. So let me just go ahead and set up the table. So notice that I split up all my intervals really using this domain to help guide me. So I know that I have these points where it does not exist. That also kind of coincides with my domain anyways. So then here at negative 1 to 1, I had to split that up from negative 1 to 0 and then 0 to 1, okay? So now let's go ahead and find our signs of the first derivative. So if I plug something like negative 2 into this, then I'm going to get something where the top is going to be positive because we'll have a negative times a negative, and then the bottom will also be positive. So this whole thing will end up being positive. So this is going to be increasing. And then from negative 1 to 0, so we're still looking at at a negative number that I'm plugging into this. So it's going to be the same thing. This is actually still increasing on this whole interval. Then as I plug in something positive, so from 0 to 1, something negative times something positive will be something positive. And then this, so since I'm squaring everything, this whole thing's going to end up being positive. So I've got a negative over a positive, so this ends up being negative. So this is decreasing, and then the same thing for this other interval. So there's kind of the logic there. Now, I do always advocate that you write out a full sentence saying where you're increasing and decreasing. So I will summarize that, but I'm also going to clear some space so we can move on. Now, just one thing I want to address and how I wrote this out. So notice that I do have these two intervals. You do have to break them up. You can't just call this negative infinity to 0 because negative 1 is not in the interval. So you have to actually write them out like this, okay? All right, so now move on to the second derivative. So I got to use the quotient rule again. So taking the derivative of the top, this will be negative 2 times x squared minus 1 squared, and then I subtract this off, leave the negative 2x alone, and now I've got to use a good old chain rule with this guy. So let's see, I can write this as 2 times x squared minus 1. So that's taking the derivative of the outside, and then I multiply this by the derivative of the inside. The derivative of x squared minus 1 is 2x. All of this over x squared minus 1 squared, and then we square it again. All right, so now there's a whole bunch of cleaning up that we need to do here. And now we are in a situation where we actually can make some cancellations, okay?
So first, before I go any farther, I want to show you where these cancellations are. So 2 times 2 here, I'm going to just rewrite this as x squared minus 1 to the 4th. Okay, multiply those together. Okay, so here's what I want to show you. I can do a cancellation that will make my life easier. So I've got, I'm going to color code this, x squared minus 1 here, x squared minus 1 here, and x squared minus 1 here. That is the relationship that you are looking for. So what is the smallest amount of x squared minus 1s we have in these three? This is the smallest amount, right? So I can cancel out one factor of x squared minus 1 from all of these. And this can be just canceled out entirely, okay? So that's going to make my life a lot easier because now I've got to multiply all this stuff together. So as I multiply this, this becomes negative 2x squared plus 2. And then let's see. I've got negative 2x times 2, so it's going to be negative 4x. And this becomes 8x squared. So this will be negative 8x squared times negative 1. So this becomes plus 8x squared over x squared minus 1 squared. So we still have some work to do here. So let's see, this becomes 6x squared plus 2 over x squared minus 1 squared. And then I could rewrite this as, I could factor a 2 out of the top and call this 3x squared plus 1 over x squared minus 1. Oops, and this should have been 3's. Sorry. These are 3's. Okay. So there I've got that. So I definitely need to make some space. Okay, so now we're thinking about inflection points here. So, you know, as far as where does the top equal 0? So this is something squared plus 1. The top's never going to equal 0, and then we have that this does not exist. We know that this does not exist at x equals 1 and x equals negative 1. However, these can't be inflection points, right? Because they're not even in the domain. So you can tell just by looking at this then that there actually are no inflection points. We just want to state that right now so that we don't throw ourselves off. Now I do need some more space here so we can finish this. So let me make some space. So even though I already know this has no inflection points, I still want to make my table. So let me set that up. Okay, so here's everything. I guess this should really say y double prime, not f double prime. Okay, so now as I'm working towards this, so if I were to plug something, let's say negative into this, so if I plug something negative into this, the top will still be positive, right? Because when I square this negative thing, it'll still be positive. And then the denominator, this will be something greater than 1. And I'm squaring that, and then I'm cubing that, so this whole thing will end up being positive. So this will be positive, and so let's see, then the conclusion here is this is concave up. Now something interesting that's going to happen is, so if I choose something now between negative 1 and 0, so when I plug that in, so if I put something smaller than 1 and square that, and then subtract 1 away, this will end up being negative, and it will stay negative because I'm cubing it. So and then the top will still end up being positive. So I have a positive over a negative. So this ends up being negative. So I'm going to have something concave down in this case. Okay. And then let's see. Actually, I didn't need to create this other interval. I didn't need to make this because this was not a inflection point. This is actually one of our critical points. But maybe just to bring this analogy home, what happens if you accidentally draw an extra interval like I just did? So if I choose something between 0 and 1, the same thing happens. The top will still be positive, the bottom will still be negative. So this all stays the same. So this is still concave down. So this also helps us to kind of trust our little choosing intervals thing, if you will. And then if I choose something greater than 1 and plug it into this, so then I go back to being positive. So this will be concave up. But like I said, we have no inflection points. And so you should write a sentence just summarizing what's concave up, what's concave down. So let's see, I will do that. So there's a summary of my concave up, concave down. So now we can go ahead and graph this. Okay, so let me draw some graph paper. Okay, and so one thing that we need to know is definitely the value of our critical point. So I should probably plug in y of 0. So if I plug y of 0 into this, I will end up getting -2 over -1. So this will equal -2. So I know I have the point then 0, -2. So let me just maybe mark some of those in. Just kind of drawing this real time. Okay, so there's our critical point. And I want to go back to this. There was actually, I missed a point here. So 0, so notice at 0 we go from increasing to decreasing. So 0 should actually be, I forgot to mention this at an earlier point. 0, let's see, 0 is a maximum, right? Because we go from 0 increasing to decreasing. Okay, so good to know. Now we also know that we have some asymptotes here. We have some asymptotes at -1 and 1. So I'm just going to draw those little guidelines for myself. Okay, and so now I should be able to graph this. So I know that I need to be, let's see, I'll come back over here. I need to be increasing from -infinity to -1 before I hit that asymptote. I also need to be concave up. Now, if you're not sure of how to actually graph this, you can also look at the end behavior here. So in this case, I'm looking, what happens as x approaches -infinity for this guy? Do I have any other asymptotes? So if I divide everything by x squared, what I will get is -1 minus 2 over x squared over 1 over 1 minus x squared. So this will actually come out to -1. So I have an asymptote also at y equals -1. So I can mark also that right here. And then if I do this again for, let's say, just positive infinity, I'll actually get the same asymptote. So I just wanted to note that before we go much farther. Okay, so now so if you're still not sure where to start, do you graph above this asymptote or below? You can always just plug in a test point, right? So if I plugged in something like -3 into this or whatever, I would find that at -3, this would be pretty close to -1. So I'm also going to be above -1. So that kind of also tells me then that the behavior in this case is going to work like this. So here I am, always increasing concave up. Okay, so now I move on to this next interval. So this has to be my maximum, okay? So nothing can go above this. Even though I have this asymptote here, I'm not going to get close to it. So I need to go from increasing to decreasing and stay concave down the whole time, which I did. And then here I'm going to have the exact same behavior. Because again, remember, I also have to be even. So this is now even. That helped me figure out how to draw this. I've maintained all my asymptotes. I'm all good to go here. So here is how that one gets graphed. So lots of pieces to kind of consider with that. So for number 6, so we have y equals x to the 1/5. Okay, so let's just start by noticing the domain. So the domain in this case is all real numbers, so that just helps me with all the other work that I have to do. And then, as I keep saying, I always like to actually figure out just what is the deal with symmetry for my functions before I go any farther, because it helps me to figure out what the graph should look like. So in this case, if I were to plug in -x, I get -x to the 1/5. So what this tells me, this is equal to -f of x. So this is going to be an odd function. Okay, so let's clear this out. And now let's go ahead and we'll find critical points and intervals of increasing, decreasing, and all that good stuff. So first finding y prime. So what I'm going to get is 1/5 x to the -4/5, which I could also rewrite as 1 over 5x to the 4/5. And so I need to figure out my critical points. So this function does not exist at x equals 0, right? We'll get a 0 in the denominator. We can't have that, so that's going to be my only real critical point. So now I need to go through and determine my intervals of increasing, decreasing. So let me set up the table. Okay, so now, oops, I wrote sine of y prime. Okay, so here's my table, so you can, let me close that as well. All right, so you can just make sure your table kind of aligns with mine. So in setting this up now, so if I choose a negative value, what is the value of my first derivative going to be? Well, you do have to think about this, right? So if I plug in something negative, the way that the rational exponents work, so first I take the fifth root of that, and then I take it to the fourth power. Now, in taking a negative number to the fourth power, this comes out to be something positive. So the sign of the first derivative will be positive, so it means we're increasing. And then also, if I plug in something positive in this, this will still be positive. So this whole thing is really increasing. But when you're summarizing this, you do have two different intervals. So I'm increasing from negative infinity to 0, and then 0 to infinity. So 0 is neither a maximum nor a minimum, but maybe something is happening there. We will figure that out. Okay, so let's clear some space. And now I'll go ahead and find the second derivative. So if I take the second derivative of this, this will be negative 4 over 25 x to the negative 9/5. So I could rewrite this as negative 4 over 25 x to the 9/5. So once again, if I'm just looking for like where does this not exist? So this derivative does not exist at x equals 0. So let's try to figure out what's going on there. So all right, I'll set up my table. Okay, so here's my setup. And so now if I start plugging things into this, so if I plug something negative in here, well now in this case, this is kind of interesting. If I plug in something negative, so now I'm going to take the fifth root of that, which will still be negative, and then I take it to the 9th power, which will make this still negative. So if I plug something negative into this, this will still be a negative value, times this negative 4 over 25th, like this is another negative number. So the sign of y double prime then will be positive, so this is going to be concave up. And then for if I plug something positive in, so this will be something positive times something negative, so then the value of this will be negative, so this is going to be concave down. Okay, so there's my other part. So let's see, I need to clear some space. Let's see, maybe I'll just summarize. Concave up. I kind of just put this wherever I can because I'm kind of constricted here with space. Okay, so there's my information. So what that tells me then is that 0 is an inflection point, right? So we can also note that. So let me make some space and note all that. So this is kind of an interesting odd result, right? So we're going from concave up to concave down. We know that the first derivative at 0 does not exist, right? And this is not a maximum. So this is kind of giving you some indication that like something odd is happening with this point, something not natural to other graphs maybe that you look at. Now the only other thing that maybe we want to think about before we go any farther, we don't have a ton of information about this graph. So one thing I like to do when this happens is I like to think about like what happens with the end behavior. So I look at my limits as x goes to positive and negative infinity, which in this case, so if I go to positive infinity, this thing also just kind of continues towards infinity, right? So that gives me a little bit of sense with the end behavior. And then if I were to plug in negative infinity, I'll just get out negative infinity. So sometimes when you do your end behavior, you get something that is like very helpful. And then other times, like in this case, you get something that maybe says, okay, so it's not, there's no other asymptotes or anything like that I have to worry about. Okay, so let me set up a table or a graph. Okay, so the point 0 is maybe the only point I can graph from like my critical points, right, or my inflection points. If I plug 0 into this, I get the point 0, 0. Then I can also plug in 1 and negative 1 and get some values out. So if you know what the graph of x to the 1/3 looks like, this is going to be very similar, but it's going to be just a slightly different shape. So as I graph this, so it's going to have, I want to have a slant here and kind of go up and over. So I want to just show you kind of what I did that I think is very significant. So right here at 0, 0, so we need to make sure that we draw this in such a way so that the first derivative does not exist. And so in this case, with how this is set up, so 0, we can plug 0 into this, right? 0 is in the domain. It's just that the first derivative at 0, that's where the derivative does not exist. So what that's telling me, and then also that's an inflection point. So here I'm concave up, here I'm concave down. So all of that information is telling me that really what I have here is like a vertical tangent line. So I need to just have that reflected in the graph. So at this point here, I would have that vertical tangent line. That would be a situation where the first derivative does not exist. So when you run into a situation where the first derivative does not exist, you want to make sure that's reflected in your graph. Okay, so moving on to 7 here. So I've got f of x equals the natural log of x over the square root of x. So if I first start by thinking about my domain, so this is kind of interesting because now you've got both the natural log of x and then the square root of x. So just as a reminder, so the domain of the natural log of x goes from 0 to positive infinity, and then the domain for the square root of x goes from 0 to the square root of infinity. So you really want to take like the intersection of these two domains. So in this case, my domain is going to go from 0 to infinity. So we can't include 0 because while I could include it here, I can't include it here. So hopefully that makes sense. Okay, so let me make some space. Now, if you watch some of my other explanations, you also know that I usually like to determine symmetry. I can tell just by looking at this that this will not have any symmetry, so we can skip over that for this one. And so now let's go ahead and find the first derivative. So we're going to have to use a quotient rule here. So in using the quotient rule, so first I take the derivative of the top function, which is 1 over x, and I multiply that by the bottom function. Then I subtract this off and I multiply the top function by the derivative of the bottom function, as shown. And then I take the denominator squared. So we've got to clean all of this up now and make this look much nicer. So what this turns into is I've got f prime of x. So let's see, this is going to become 1 over the square root of x minus the natural log of x over 2 times the square root of x. All of that over x. Okay, so now if you've watched some of my other videos, you should know that I do not like having these denominators, these fractions here. So now what I want to do is I want to get rid of those. To me, the best way to do that is just to multiply everything by the least common denominator. So I'm going to multiply everything by 2 times the square root of x. Whatever I do to the top, I also have to do to the bottom. So I need to multiply all of this out as shown. So in doing this, what ends up happening, so here, the square root will cancel out and I'm just left with 2 on top. So the 1 will turn into a 2. And then here, this will just drop out entirely. And so then I just have, let's see, then I just have 2 minus the natural log of x, and then this will be x, 2x to the 3 halves. Okay, so there is my simplified first derivative. So let me make some space. Okay, so just looking at this, I can see that the first derivative does not exist at x equals 0. However, if I pause now and remind myself what is the domain, well, that's fine. So I don't have to worry about this, right? The fact that this does not exist at x equals 0 doesn't belong in the domain anyway, so whatever. So now I just have to think about where does the top equal 0. So if I take 2 minus the natural log of x equals 0, so now you're going to have to flex some of those pre-calc skills. So what I get is the natural log of x will equal 2, and then I have to use the definition of the natural log of x. So I'm going to take this as this will be x will equal e squared. That's just using the straight up definition of a logarithm to help me solve this. So, okay, so there is my other critical point, x equals e squared. There is my critical point. Okay, so I'll clear some space and I'll make a table. All right, so here's my table. So now if I start plugging values in, so remember you're just trying to determine the sign of f prime here. So if I were to plug something like e to the first in, so remember the natural log of just e will equal 1. So on top we have 2 minus 1, and then the bottom, so this will be positive, the top will be positive, the bottom will also be positive. So the sign of this will be positive, so this is going to be increasing. And then if I choose anything over e squared, then taking the natural log of e to the whatever, e to the fourth, that'll just give me the value of the exponent. So just to write that out for you. So the natural log of something like e to the fourth. So this is really equal to 4 times the natural log of e, so this just equals 4. So just a reminder of those logarithm properties for you. So anyways, so that makes the top negative and the bottom will still be positive. So the overall value of this will be negative, so this will be decreasing. So we are increasing from 0 to e squared, and we are decreasing from e squared to infinity. So, okay, let's clear some space. And now we'll find the second derivative. So taking the derivative of the top function, this will be negative 1 over x, and I multiply that by the bottom function, and then I subtract that off, and I leave the top function alone, and then I multiply that by the derivative of the bottom function, which will be 3x to the 1/2. That's the derivative of the bottom function, and then take all of that 2x to the 3/2 squared. So now if I simplify this, let's see, what do I get? I will get negative 2x to the 1/2 minus 6x to the 1/2 plus 3x to the 1/2 times the natural log of x, all of that over 4x to the third. Okay, and so now you'll notice, maybe I'll just simplify this one step farther. Let me make some more space. All right, so if I simplify this one step farther, so I get negative 8x to the 1/2 plus 3x to the 1/2 times the natural log of x over 4x cubed. So you'll notice I have x to the 1/2, x to the 1/2, and then x down here. So I can cancel out a factor of x to the 1/2, so that's what I'm going to do. So this becomes f double prime of x equals negative 8 plus 3 times the natural log of x. And then, okay, so 3 is equal to 6 over 2. So if I want to subtract off the 1/2 from this, this will become 4x to the 5/2, all right? And so there is my second derivative. Okay, so now in looking at this, so I can see that once again, so this second derivative does not exist at x equals 0, but for the same reasoning from before, 0 is not in the domain, so that doesn't matter. So I really just need to concern myself with where does the top equal 0. So if I take negative 8 plus 3 times the natural log of x equal to 0, so let's think about that. That can be simplified to the natural log of x will equal 3 over 8. So what I get then is x will equal e to the 3 over 8. And, oops, wait, sorry, this should be, sorry, went a little fast there. This should be 8 over 3. 8 over 3, and then x equals e to the 8 over 3. Okay, so there is my possible inflection point. So going back to where we were at, so let me clear some space, and let me note that that's a possible inflection point. So there I've summarized the information, so I'll make my table. Okay, so now in setting this up, so if I take something like, I don't know, e squared, so if I were to plug that into this, so just as a reminder of kind of how the math on that works, so I have negative 8 plus 3 times the natural log of e squared, so this would equal negative 8 plus 3 times 2, so this ends up being something like negative 2, so that's negative. So that's the way you can figure that out. And so then this is going to be concave down. And then if I choose something over the value of e to the 8/3, this will end up being positive. So then this will be concave up. Okay, so I will just erase this over here and just summarize that real quick for us. So I've got my summary there, and let me clear out the table so we can graph. Okay, so for this particular graph, so I'll just do this as 2's, so I'll just note that here. Okay, so plugging in my critical points, I'm kind of running out of room here, but if I were to plug in e squared into this, so e squared is like just under 8, and then if I plug e squared into my original function, So what I get is the point, I will get e squared and then 0.736 if I round. So if I graph that, it's going to be like somewhere over here. Okay. And then for my other point, e to the 8/3, so if I plug that in, this will come out to 0.703. And let's see, I actually need a few more tick marks, so that'll bring me somewhere around there. Okay, so this is kind of a difficult graph to draw. But remember, so my domain starts at 0. So this is my domain. I need to take that into account, and then I need to be increasing from 0 to e squared, so about here, and then decreasing from there on out. And I'm going to be concave down from 0 to this e to the 8/3, and then concave up otherwise. So let's see, maybe I should move this graph over a little. So there, I just shifted the graph over. Okay, so now I want to be increasing up until that e squared point. So increasing. And so now, this is going to look very subtle, honestly, just from the scale that I have. But I need this to continue to kind of stay concave down until I get to this point, and then I'm just going to ever so slightly, like, so keep this decreasing, but kind of go from this concave down to a concave up type ordeal. But it's not going to look like much. I will kind of also mention that. So I'm concave down, and then I'm concave up. So if you even try to look at the graph of this, it's very, very subtle in my opinion, of like how like the graph just kind of looks like part of a like a rational function or something. So this is kind of an odd looking graph. It's a tough one to draw, but this will kind of pick up what we were looking to do. So that covers that one. All right, so number 8. So now we want to identify the domain. So the domain in this case is going to be all real numbers. And then, as you know, I like looking at symmetry, so I always like to just plug in negative x. It just kind of tells me what the graph, like a general idea about the graph before I get too far into the problem. So if I were to plug negative x into this, so in this case I would get the cube root of negative x cubed minus 1, so there's no symmetry in this case. So no symmetry. So now we can start working towards finding critical points and first derivatives and all that good stuff. So let me clear this out. Okay, so let's start by finding y prime. So I've got to use the chain rule here. So this will be 1/3 x cubed minus 1 to the negative 2/3, all of that times the derivative of the inside, which will be 3x squared. So now I just want to simplify this as much as I can. So this will become x squared over x cubed minus 1 to the 2/3. And so now, looking at this, so where will this equal 0 and where will this not exist? So this does not exist. This first derivative does not exist at x equals 1. So if I plug 1 into this, I will get a 0 in the denominator. And then also this will equal 0 at x equals 0. So those are my 2 critical points. And so now I can set up my table, so I'll go ahead and do that. Okay, so now and you can double check that your table matches mine. I just wanted to pop that on the screen to save time. Okay, so now we start doing our interval testing. So if I choose something, I don't know, negative. So if I choose something negative and I plug it into this, so something negative squared, this will be still positive. And then this, so now you have to kind of just be careful when you think about plugging something negative in. So if I plug something negative in, the bottom part, this will be negative, but then I take that to the 2/3. So remember the way that these rational exponents work, you take the cube root followed by squaring it. So no matter what, you end up like squaring the whole thing. You see what I'm saying? So because of that, what you end up getting then is something positive. And so that actually really dictates then what's going to happen for this entire problem. So this is increasing. So no matter what, so notice that on the top and bottom, I'm squaring the top, and at some point I'm squaring the bottom, right? So it doesn't actually matter what we put in. This is always going to end up being positive. The top will always be positive. The bottom will always be positive. So the whole table is positive. So you do have 3 separate intervals though. So sometimes people then want to say, oh, it's increasing on this domain. It is not. It is increasing on these 3 separate intervals, okay? So let me clear some space and note that. Okay, so it's just always increasing. So now let's move on to the second derivative. Okay, so now to take the second derivative of this, I'm gonna have to use a quotient rule. So this is gonna be a little bit of a nastier derivative. Okay, so taking the derivative of the top, that'll just be 2x, and then I leave the bottom part alone, and then I subtract this off. I leave the top part alone, and now I have to take the derivative of the bottom, so I have to use a chain rule here. So this will be 2/3 x cubed minus 1, and then this will be to the negative 1/3, and then times the derivative of the inside, which will be 3x squared. All of this divided by the denominator, all of this squared. Okay, so I obviously am going to need a lot more room for this, so let's clear some space. So now you've got to do some heavy lifting, a little bit anyways, with the algebra. So in simplifying this as much as I can, so I'll just leave this as 2x x cubed minus 1 to the 2/3, okay? And then here, so let's see, what is this going to become? It looks like the 3's drop out at least, and then otherwise this will be 2x to the 4th, so I add the 2 exponents, over x cubed minus 1 to the 1/3, and then all of this over x cubed minus 1, and we'll now call this to the 4/3. Okay, so if you watch my videos, you know that I always like to get rid of the denominators, so I'm very methodical in kind of how I cancel everything out. So I now am going to multiply the same thing on the top and the bottom. So what this will allow me to do is I can just cancel this denominator out entirely, and then I will add 2/3 and 1/3 when I distribute here. So now instead of this being to the 2/3, this will just be to the first power. That'll be it. So this actually simplifies quite a bit now. So now I've got 2x times x cubed minus 1 minus 2x to the 4th. All of that over, let's see, what does this become? X cubed minus 1 now to the 5/3, right? Okay, so now we've really just got to like work this out as best we can. So do not do not cancel these out, right? You cannot cancel these out. You could cancel these out if you would x cubed minus 1 here and here, but you don't. So you can't cancel them out. Okay, so that is like a big math teacher pet peeve. All right, so what I'm going to do instead is I'm going to distribute this so that I can collect like terms on the top. So I need to make a bunch of space. And I'm just going to continue working this out very methodically. Okay, so good news, those 2x to the 4th are going to drop out. And so now I'm almost done. So my second derivative now is just negative 2x over x cubed minus 1 to the 5/3. Okay, and so now I can go ahead and determine possible inflection points. So we'll say maybe inflection points, maybe. So we're going to look at x equals 0, and then x equals 1, right? Okay, so let's go ahead and make our table. So I need to clear a bunch of space. So let's see. I'm actually going to write inflection points. So we're looking at x equals 0 and x equals 1. So I've got space. Now I'll make a table. Okay, so now as I start plugging things in, So if I plug a negative number into here, so what's going to end up happening, I have a negative times a negative, which becomes a positive, right? And then here, so if I plug a negative number into this, this will be negative, and then taking this to the 5/3 will keep it negative. So I have a positive over a negative, which would make the whole sign negative. So this is going to be concave down. And then if I take something like 1/2, okay, 1/2, so the top will be negative, and then the bottom, so if I plug something like 1/2 in, this will end up being negative, right? So then I'll have a negative over a negative, so this will be positive, so this will be concave up, and then this last one, so if I plug something positive but greater than 1, the bottom's going to be positive, the top's going to be negative, so the whole sign will be negative, so this will be concave down. Okay, so let's go back to where we had all that other information and summarize this. So let's see, I'm going to replace this with my second derivative and my concavity. So there is everything. Oh, and gosh, let's go back to that table one more time, sorry. So what I see here actually also is that 0 and 1 are inflection points, right? So we have an inflection point here, and we have an inflection point here. So just a thing to note with that. So 0 and 1 are neither maximum nor minimum, but they're both going to be inflection points. So now, maybe I should just note that. So x equals 0 and 1 are inflection points. Okay, so now let's go ahead and graph this. So I need just a new slide entirely. Okay, so now I have my graph, and I've just noted over here, so those are my two inflection points. So if I plug them back into the original function, so y of 0 is going to give me -1, and then y of 1 is going to give me 0. So if I plot both of those, so I've got a point here, and then let's see, 1, 0. So I've got those two there. So the whole thing needs to be increasing, right? And then I need to have inflection points here and here. And so I need to be going really concave down, and then from here to here I need to be concave up, and then from here on I go concave down. So how will that look? So the way that can look then is I'm going to go down, up, down. It's kind of a funky looking function, right? So neither one of those are maximum or minimum, right? This just continues to go up. And so they're just inflection points. They don't have like that hump that you need for a maximum or minimum. So that covers that one. So for number 9 and 10, so the directions here are that we have y prime, and we have to find y double prime and then sketch what a graph could be. So okay, in this instance, so I've got y double prime. I can really easily find the second derivative, right? So from this information, what is the best graph that we could possibly sketch? It's not going to be the exact graph because we don't have the original function, but we can sketch out something that is probable, right? So like what I notice in looking at this, so like for instance, this will factor as x minus 3, x minus 1. So I have critical points at x equals 3 and x equals 1, right? I know that just by looking at that. And then looking at this one here, so if I were to set this equal to 0, I would have a possible inflection point, put a question mark, at x equals, 2. Okay, so from this information, like I said, we only have so much to go off of here, but judging from the first derivative, it looks like the domain could be all real numbers. So I'm going to just say, if the domain of this is all real numbers, what can I do in terms of like my intervals of increasing and decreasing? So if I were to set up those intervals, so I'm going to go from -∞ to 1, 1 to 3, and then 3 to infinity. Okay, so I can still come up with these intervals, right? And let's see, I'll just extend all of this down. Okay, so if I were to plug something like 0 in to the derivative here, this would be positive, so I'd be increasing here. And then between 1 and 3, so if I choose something like 2, this would be something negative times something positive, so this will end up being negative, so this will be decreasing. And then for the final part, this will be increasing again. So I can say something now about the intervals, and also now it looks like 1 and 3 should be extrema, okay? And then at the same time, let's see, I think I have just enough space to create another table. I mean, it's going to be a little bit of a stretch here, but I'm going to do my best. Okay, so if I create a second table going around that inflection point, there would be my intervals. So now if I take something like 0 and plug it in here, this will be negative. So I know I'm going to be concave down. And then if I choose something greater than 2, this is going to be positive. So this will be positive, so this will be concave up. So even though I don't know the exact points, I actually get quite a bit of information about this graph. So you're going to have this in front of you on your paper. I'm going to summarize this to this side, so let me make some space and summarize. So there's kind of all my information, and then I'll draw a graph. Okay, so I'm going to be very ambiguous in how I set this up, actually. I haven't put any y, like tick marks here, because I can't figure out what the y is. The only thing I can really speak to are my x's. So I know at x equals 1 and x equals 3, I have critical points, right? And then I know at 2, I should have this inflection point. Now, one thing I didn't mention, which I probably should have, was, so for 1 is also a maximum, and then 3 is a minimum, right? So I want to mark these. So 1's going to be my maximum. Here's 3. I want that to be a minimum. And then somewhere here at 2. So yeah, I have plotted 2 here at 0, 0. So remember, the idea behind this is just to create a possible graph. It doesn't have to be the graph. So I just kind of set these up so that, you know, I can match what my intervals of increasing and decreasing are. So now I know all the way up to, let's see, all the way up to 1, I need to be increasing. And then from 1 to 3, I need to be decreasing, with 2 being an inflection point. And then from 3 on, I need to be increasing again. So this would be a good potential sketch of the graph. Now, if you didn't go through this point here, maybe your graph was a little bit raised. Maybe your graph looked more like, your graph could have also looked like this. That would have been fine, or maybe a little bit lower. It doesn't matter. It's just about getting that possible graph. So this is what would work. All right, so for number 10, so we've got y prime is given, and we are going to find y double prime and then sketch what a possible graph should be. So I do want to point out here, so we've got y prime is secant squared x. So notice that in this case we do have a restricted domain, and actually, so at pi over 2 and 3 pi over 2, this function does not exist, so it's nice that this was restricted. So let's go through and, let's go ahead and find y double prime. So to do that, we're going to have to use the chain rule. So just as a reminder here, this is equivalent to, I'll just write it on the side, secant x squared, right? Those two things are one and the same, so you have to use the chain rule for this derivative. So I start with using the power rule on the outside function, and then I multiply this by the derivative of the inside function, which will be secant x tangent x. Now, here's the thing. I think that this is kind of difficult for people to think through. It's like one of those things where people don't think of secant or think through secant and tangent on the unit circle. So you might find it helpful to actually rewrite this now in terms of sine and cosine. So I could rewrite this as 1 over cosine squared x times sine of x over cosine x. And this is just going to help me to think through like my inflection points and whatnot a little bit easier, if that makes sense. I can think through this much more quickly than I can secant and tangent. Okay, so I've got that second derivative, so let me make some space. Okay, so now let's work on finding things like critical points and just get as far as we can with this. So for secant squared x, so remember that's the same thing as 1 over cosine squared x. So just looking at this, there is no place where this will equal 0, right? Because the top is equal to 1. So the top will never equal 0, so the whole function cannot equal 0. However, we get a 0 in the denominator when x is equal to, well, really pi over 2 or 3 pi over 2, which we can't use. So in this case, there are no critical points. So this totally matters just because of how our domain was restricted. If we had a different domain, then you would say that this does not exist at certain points, but that is not the case for this problem. So now let's just figure out increasing, decreasing. So I'll set up my table. So if I choose any value in this domain, since I'm always squaring that value, this will always be positive. So this function is just always increasing, okay? So I'm just going to note that here. Always increasing. Okay, so let me clear some space. And now let's think about potential inflection points. So here, so I will have a 0. So let's see, I'll say this is 0 at x equals, so what value of x? Just pi. So the whole thing will equal 0 when we have sine of pi. And then otherwise, so I'm not going to get a 0 in the denominator because the only places where I would get the 0 in the denominator are pi over 2 or 3 pi over 2, which is not part of our domain. So this is the only possible inflection point, this pi right here, okay? So let's set up another table. So now, going from pi over 2 to pi, so if I just think about that quadrant in the unit circle, so all the y values will be positive and all the, all the y values in that quadrant are positive. That corresponds with the cosine. Or is that, let me say that one more time. All right. The y values are positive. That corresponds with the sine value. So all of the values in this interval will be positive. But all of the x values in that quadrant from pi over 2 to pi, you might want to have the unit circle in front of you. Those will all be negative, and then I'm cubing those. So here, this is all going to be concave down. So the sine of y double prime will be concave down. So we are concave down. And then from pi to 3 pi over 2, so now we have that both the x and y values in that part of the unit circle are going to be negative. So I have really a negative over a negative, which will give me a positive overall. So this is going to be concave up. So what that means then is pi is an inflection point, okay? So let me clear some space. And now I'll make a graph. Okay, so my graph needs to go from pi over 2 to 3 pi over 2. So as I said in the last problem, so you don't have to be exact with your points here. There's no way for us to figure out the y coordinates. So really what I want to just make sure of is, so here is where my pi might be. I'm just going to make this an inflection point. And then this thing just has to always be increasing. So the best I can really do here is something like this, increasing. Boom. And so if you think about this, this makes total sense. This is probably related to the tangent function. So this would be a very realistic version of the graph. So this is good enough for our purposes. So number 11 is an optimization problem. Find the dimensions of a right circular cylinder of maximum volume that can be inscribed in a sphere of radius 20 centimeters, and what is the maximum volume? So just in case you forgot, so I have just the two situations up here. We actually really only need to know something about the right circular cylinder, but I just figured I'd kind of throw this down and remind you of how a sphere works as well. So we've got this sphere of 20 centimeters, and we're trying to put a right circular cylinder, I like to think of it as a can, inside of the sphere. And so we know that this is the volume formula for our right circular cylinder, but our life would be easier if we could get this down to two variables. I cannot optimize this equation as is because it has too many variables. So if I could figure out some clever way to get rid of a variable, then my life will get much easier. And so this is now where the sphere is going to come into play, but I think it's a little bit tricky. So what we're going to do is we're going to think about how can we rewrite h. So okay, so going back to this, so like I said, this is 20 centimeters all the way around. So I want to think about, like, I'm going to try to draw this in a way, like you're going to have to visualize this a little bit. So let's think about this point here. And it's very hard for me to make this like totally work, but what I'm trying to get at is, like, if I were to think going like back maybe somewhere towards the center of this sphere and up, you can probably visualize there is a right triangle kind of formed within this sphere, right? So that's what I'm trying to represent here. So try to take a second and just imagine this right triangle. This has kind of been pushed back, so that's why it looks a little bit weird. but hopefully you can imagine that, because once you imagine that, the rest of this starts to get a bit more approachable, I guess. So I want to think about the coordinates of this point here, but like in a 2D form. So this really just looks like a circle in 2D, right? So for a circle, I have that equation x squared plus y squared equals r squared. So I just want to think about this situation for a moment, and then we're going to retranslate it to our problem. So in this situation, if we're thinking about this like 2D type shape, so like I said, my radius is 20, so I can technically kind of get to the y value of this, which helps me get to the overall height of this cylinder. So if I can figure out the y value, that's going to give me like this little segment here, if that makes sense to you. You've got to really kind of think about going from that 3D form to the 2D form. But if I were to solve this, so here would be my equation for y. So this would get me from here to here. This is talking about just half of this cylinder, right? Because we're going from the radius up to the top of or up to this point on the sphere. So if I want to get the entire height of this can or cylinder, then I would just multiply that by 2. And then now that gives me the whole height. Now, I changed all of this to the context of just trying to figure this out. So I've written this as 2 times the square root of 400 minus x squared. But in the context of our problem, notice that we don't have any x's. So instead of thinking of this in terms of x's now I'm just going to translate this back to being an r. So I know that's kind of a lot of variables I've thrown around, but hopefully you kind of get where I'm going with this. If not, leave me a comment and I'll try to explain it a little bit better. Okay, so I'm going to replace this h now with that whole thing that we just found. And like I said, we wanted to just leave this all in terms of r squared. So the value of the r is kind of dependent on the application. But now, okay, so now we can optimize. So now it's just like smooth sailing from here. If you consider smooth sailing to be kind of difficult first derivatives. So okay, here's my function. I'm going to take the first derivative. I've got to use the product rule. So you can pause the video. I highly recommend from this point on that you just try to finish this problem, and I'm going to show you all the steps. So this was my work with the product rule, and now I have to just like simplify. So in simplifying this, so I get this like 2-part problem. I want to have everything over a common denominator. So if I get a common denominator, here's where my problem would lead me to. Now I need a little bit more space, so I'll clear some more space, and I need to continue to work all of this out. Okay, so I'm going to work all of this out as shown, and then I can collect my like terms as shown. And ultimately, I'm trying to find critical points here, so I want to factor out the top. So I'll just give myself a little bit more space one more time. And I can factor negative 2 pi r out, and I am left with this problem here, okay? So you can rewind the video and look at all the steps if you need to see the work. It's all laid out there for you. But now what I want to do is I want to find my critical point. So I just want to note here, like normally I talk about this a little bit earlier, but just for my radius, obviously my radius has to be something greater than 0 and less than 20, because right, that's the largest radius of our sphere. So in solving this, so I find either that the top will equal 0 when r is 0, or we could also have, if I solve this guy here, instead of equal to 0, I will get the square root of 800 over 3, which is about this decimal here. Okay, and so now what I can do is I've really got like all the points that I need, and maybe you would also say, oh, 20 is a point because it makes the denominator 20. So it doesn't matter if you include 20 or not. So 20 and 0 will both give you 0, so those are not going to be the maximum. I think we kind of intuitively know that. So our maximum is going to occur at the square root of 800 over 3. And so that will be our maximum volume. And then I have noted in the answer key, so then you also just have to plug this in and you will get to your height. Because remember, you have to find all the dimensions as well. But that covers this problem. So for this final problem, so I have something that's even more like open-ended as far as sketching a graph. So it's sketch a graph where all of these conditions hold. And this is really a great way to test how well you understand concavity, increasing, decreasing, just from like the pure definitions. So this is saying that the function is increasing, right? it's greater than 0. The first derivative is greater than 0 when x is less than 1. And it's decreasing when x is greater than 1, which tells us that x must be a maximum. And then it's going to be concave up at after 3 and concave down before 3. So we just need to get a shape here. So I've drawn just a little sketch of a graph and I've made little tick marks. It doesn't matter where your y coordinates go. You don't even necessarily need to have these tick markers. For me, I just find them helpful. So I know at 1, I need to make this maximum. So I'm just going to make a higher point here. And then at 3, I need to have this inflection point change. So before 1, I need to be increasing. After 1, I need to be decreasing. I need to stay decreasing. But then at 3, I need to go from being concave down to concave up. So after 3, so you have to kind of keep these directions straight. When x is greater than 3, we are concave up. So maybe we'll just draw like a little thing like that to make sure I'm concave up. And then I'm going to go increasing, and then there we go. So now I'm concave down all the way here, and then I just go concave up, and that is a good little micro sketch of a graph. So when you get problems like that, they are intended to be a little bit more open-ended, but they're really there to see if you can read this information and interpret it for a graph. And so otherwise that covers it for this video, guys. So this one actually took me quite a bit of time to create. So if you found it helpful, please consider leaving me a comment or hitting the like button or hitting subscribe. And otherwise, thanks for watching, guys. I'll catch you next time.